Hey everyone, ready for another deep dive? You guys sent in some seriously cool research on white dwarf stars, and, well, let's just say we're about to uncover some pretty mind-blowing stuff. Imagine this. Scientists are looking at thousands and thousands of these stellar remnants, and they're finding something completely unexpected.
Yeah, what's really got everyone buzzing is this. Hotter white dwarfs. They seem to be, well, puffier than cooler ones.
Puffier.
Puffier.
Yep.
Even when they have the same mass, it's really making everyone rethink what we thought we knew about these super dense objects.
Okay, before we get too deep into that, maybe we should start with a little white dwarf 101 just to make sure everyone's on the same page.
Okay, sure.
What exactly are white dwarf stars?
So think of it this way. A white dwarf, it's like the leftover core of a star.
Okay.
Like our sun, after it's burned through all of its fuel.
Right.
It's the star's dying ember. But what an ember! Imagine squeezing the entire mass of the sun,
Wow.
into something the size of Earth.
The size of Earth.
That's how dense a white dwarf is.
Oh, wow. So you're telling me, like, a teaspoonful of white dwarf material would weigh a ton.
A ton, that's right. And it's because of this insane density that white dwarfs give us this unique opportunity to see how gravity and physics work at a scale we just can't replicate here on Earth.
Yeah, no kidding. So we've got these crazy, dense, super compact objects, and now we're finding out they're not all the same size.
Oh.
What did this study actually find?
So researchers, they looked at a massive amount of data, 26,000 white dwarfs.
26,000.
Yeah. And they focused on how gravity affects the light they emit. This is something called gravitational redshift. And what they found is that the hotter white dwarfs, even though they have the same mass as the cooler ones, appear slightly larger.
So they're expanding as they heat up.
It's like they're inflating. And, that seems kind of counterintuitive.
Yeah, I was just going to say that. It seems like the hotter something gets, the more it would expand.
Right.
And I don't know, like steam rising from a boiling kettle.
Yeah, exactly. It's that unexpected nature that makes this finding so intriguing. It really challenges what we thought we knew about the interplay of forces within a white dwarf.
Right.
You've got gravity, of course, trying to crush the star inwards.
Yeah.
But then you've got this outward pressure generated by heat, quantum forces, all pushing outwards.
So it's like this constant battle, this push and pull.
Like a cosmic tug of war. So as the white dwarf cools, the outward push from the heat, it weakens, and gravity starts to win a little bit.
Right, so it gets smaller.
Exactly, more compact. But in the hotter white dwarfs, that outward pressure, it's stronger.
Okay.
And that's what gives them that slightly puffed up appearance, like the star is flexing its muscles against gravity's pull.
So the size of the white dwarf, is that kind of telling us about the strength of those forces inside, battling it out?
Precisely. And by studying these size variations, we can really start to understand how those forces change over a white dwarf's lifetime. It helps us refine our understanding of how stars live and die, stellar evolution as a whole.
So these puffy white dwarfs are like a window into the final chapters of a star's life.
They really are. And as we continue to peel back the layers of this cosmic onion, I have a feeling we'll find even more surprises along the way. It's pretty amazing, right? Makes you wonder what else is hiding in these seemingly simple objects.
It really does. In one of the sources you sent, it mentioned that this research, it can help us learn more about dark matter. And I got to say, my mind went straight there when I read about these puffy stars.
Yeah, it's a pretty exciting possibility. Dark matter, it's like one of the biggest mysteries in astrophysics. We can't see it directly,
right? But
we know it's out there because of how it affects galaxies and galaxy clusters with its gravity.
Yeah, it's a cosmic ghost, right? Leaving its mark on the universe, but we never actually see it.
Perfect description. Now, some scientists, they think certain types of dark matter particles, they can actually interact with ordinary matter, just very weakly. And if that's the case, white dwarfs might be the perfect place to look for it.
Oh, really? Why is that? What makes white dwarfs such good dark matter detectors?
Well, because they're so incredibly dense.
Right.
White dwarfs, they could actually accumulate dark matter particles over billions of years.
Good.
And as those particles interact with the core of the white dwarf, they could, very slightly change its density and, in turn, its size.
So it's like we're trying to find, like tiny fingerprints left by dark matter on the structure of the star?
Exactly. It's definitely a challenge, but it's not impossible. The key is you need a lot of data. You need to look at a lot of white dwarfs, and you need really precise measurements. But if we can find a pattern,
Yeah.
a correlation between the size of a white dwarf and those dark matter interactions, well, that would be groundbreaking.
I can only imagine. It would be huge for the scientific community if we could finally unravel the mystery of dark matter.
Absolutely. It would be a landmark achievement. And, it just goes to show how creative scientists can be, using these stellar remnants, these white dwarfs, as cosmic laboratories to probe the universe's biggest mysteries.
It really is amazing. Going through these sources, it's clear there's still a lot of debate about what dark matter actually eyes. What are some of the leading candidates in this cosmic?
Well, one of the most popular ideas is the WIMP. It stands for Weakly Interacting Massive Particle.
Okay.
WIMPs, they're these hypothetical particles that are thought to be heavy and slow-moving, and they only interact with regular matter through weak forces and gravity.
Oh, so they're kind of like the strong, silent type of the particle world?
Yeah, I like that. And then there's the axion. That's another hypothetical particle. But axions are much, much lighter than WIMPs. Axions, they're interesting because they could interact with light in all sorts of cool ways. Scientists are actually looking for signs of them in all kinds of astrophysical observations.
It seems like there are a lot of ideas about what dark matter could be, but actually pinning it down, figuring out what it really is, that's still a big challenge. Are there other ways, besides using white dwarfs, that scientists are trying to solve this cosmic mystery?
Oh, absolutely. It's a multi-pronged approach, really. Scientists are attacking this problem from all angles. One way is they're using particle accelerators. Really powerful ones, like the Large Hadron Collider.
I've heard of that.
They're trying to create dark matter particles directly, like smashing atoms together at crazy high speeds and seeing what comes out of the wreckage.
Sounds intense.
Oh, it is. Another approach is to look for signs of dark matter in the cosmic microwave background radiation.
What is that again?
It's like the afterglow of the Big Bang.
Right.
By looking at the patterns in this radiation, scientists hope to find clues about the early universe and the role dark matter played in shaping it.
So it's like using the universe's oldest light to try to understand one of its biggest mysteries. That's really cool.
Yeah. But for now, let's maybe get back to our white dwarfs.
Okay, sure.
Aside from the dark matter connection, what other insights can we get from these puffy stars?
Yeah, good question.
One really interesting area is their connection to the Chandrasekhar limit. It basically defines the maximum mass a white dwarf can have before it collapses. Yeah, it could collapse into a neutron star or even a black hole.
Whoa. So we're talking about the ultimate fate of these stars. Like the point of no return where gravity finally wins.
Exactly. By looking at how white dwarfs react to changes in temperature and pressure, we can fine-tune our understanding of this limit. It helps us understand the boundaries between different kinds of stellar remnants and the forces at play when a star dies.
It's just crazy to me, the power of these observations. We're talking about tiny variations in the size of white dwarfs, things that are so far away and so faint.
Yeah.
But these little differences can have such a huge impact on our understanding of, some of the most fundamental ideas in physics and cosmology.
It really shows how interconnected everything is in the universe. Even seemingly small details can lead to big discoveries. And who knows what other surprises are waiting for us as we continue to study these fascinating objects.
It really is incredible, isn't it? Just these tiny, tiny variations in the size of white dwarfs. And we can learn about these massive forces that are shaping the universe.
Yeah, it is. And it reminds us that even in these objects that we think of as, like, dead, like white dwarfs, there's still so much more we can discover. And these findings, they often challenge what we thought we knew. They really push the boundaries of our understanding.
You mentioned earlier, too, that researchers are also looking at the chemical composition of white dwarf cores. What kind of information can we get from that?
Well, it's kind of like stellar archaeology. Like, we're piecing together the history of a star by looking at what's left behind. So the composition of a white dwarf's core, it can tell us about the star's whole life, the processes that happened as it evolved, the elements it created in its core. It's really a fascinating way to trace the lineage of these objects.
So by comparing the compositions of different white dwarfs, we can kind of get a sense of like the different paths that stars take as they age and eventually fade away.
Exactly. It helps us build a more complete picture of stellar evolution, understanding the variety of these processes and how they contribute to the amazing diversity of the cosmos.
It's pretty wild to think about all the things we've learned just by studying these white dwarfs. Their density, that unexpected puffiness, the connection to dark matter, even their role in helping us understand the Chandrasekhar limit.
And who knows what other discoveries are out there. As telescopes get more powerful, our data analysis techniques get more sophisticated. I'm sure white dwarfs will keep surprising us.
Speaking of surprises, one thing that really stuck with me from these sources was this idea that we really need to have a strong understanding of, normal physics before we can really recognize the weird stuff, the really unusual things.
That's a great point. It's crucial, really. By understanding how things work under, normal circumstances, it gives us a baseline. Then we can measure the things that are different, the anomalies, the things that deviate from what we expect. And those are the clues that often lead to new discoveries and a deeper understanding of the universe.
So it's not just about what we know. It's about knowing when something doesn't fit the pattern, when something challenges what we thought we knew. Right.
Exactly. Those are the things that make scientists curious. Those are the things that push us to ask new questions and search for new explanations. That's the heart of scientific discovery.
So as we wrap up our deep dive today, is there a final thought or question you'd like to leave our listeners with? Something to ponder as they keep exploring these really cool topics?
Well, I'd encourage everyone to think about this. What other seemingly small details in the universe might hold the key to unlocking these huge mysteries? We've seen how, just the slight puffiness of hotter white dwarfs has opened up a whole new area of research. So what other hidden wonders are out there waiting to be discovered?
That's a great point. It's a reminder that sometimes the biggest discoveries come from paying attention to the smallest details, the unexpected patterns, the things that might seem insignificant at first glance. It's about being curious, asking questions, and being open to being surprised by the universe.
Absolutely. The universe is full of mysteries, and those are the things that make it so fascinating.
Couldn't have said it better myself. Well, that brings our deep dive to a close for today. Thanks for joining us on this cosmic journey, and until next time, keep those minds curious and those stars bright.